Hello, I'm Joe Lanzoni with Lightning Eliminators in Boulder, Colorado, and today I'm here to talk about floating roof tanks, in particular, lightning, and how to make your floating roof tanks safer. Let me jump into a slide presentation. So today we're going to talk about tank fires and how tanks get ignited by lightning and what is the risk. We're also going to talk about bonding of the roof and shell and discuss how to do that. So here are some storage tank lightning facts. There are over 20 tank fires per year worldwide, and 1/3 of those are attributed to lightning. In fact, lightning is the leading known cause of tank fires. All tank fires are expensive. There's no such thing as a cheap tank fire. The point of this slide is to show you that these tank fires are extremely expensive, often measured in the millions and millions of dollars. Also, some folks believe that covered or dome roof tanks are not at risk. Well, this is simply not true. Both external and internal floating roof tanks are at risk, and you need to look no further for proof than this YouTube video. This YouTube video shows a covered floating roof tank being ignited by lightning. There's several things to consider when we're thinking about tank fires. Number one, the size of tanks has increased over time, and that means the bigger the tank, the bigger the fire. Also, as we've discussed, tank fires are very costly, not just in terms of lost material in the tank, but also business interruption, environmental damage, and damage to public opinion. And of course, the more tanks you have and the bigger the tanks, the more firefighting resources you need to have on hand. So how does lightning cause ignition? And what is my risk? Well, the next few slides attempt to answer those questions. This slide shows lightning terminating on the top rim of a floating roof tank when the roof is low. As you can see, the current flow, shown here in yellow, goes down the inside of the shell and across the floating roof and up the other side of the shell. When there's a lightning strike to a nearby location, we also have similar current flows, which means there's current flow up the side of the shell. It then arcs across the seal and across the floating roof and to the other side of the tank shell. Tank is most at risk when the roof is high. And that's because the current density tends to concentrate over a very small section of seal. So what we're trying to show here is the current in yellow is concentrated along an area where you will likely have arcs from the roof to the shell. In fact, 80% of all tank fires occur when the tank is more than half full. Now, compare the previous slide to this slide, where the floating roof is low. As you can see, the current shown here in yellow is spread out or less dense than in the previous slide. And so that means the current density over any section of seal is less, and you will be less likely to have sustained arcing along the seal when the roof is low. So here's some interesting lightning information. The average lightning strike contains 30,000 amps of current, and about 90% of all strikes contain 80,000 amps or less. There's up to 30 individual lightning strikes in each lightning flash, with the average number of strokes per flash being 4. That means every time you see lightning, there is on average 4 distinct current flows in each flash of lightning that you see. So here's a map courtesy of NASA, which shows the world's lightning strike density. As you could see, certain areas have more lightning than others. The high lightning areas across the world are shown in dark, and that would include Central Africa, Southeast Asia, Southeastern United States, and so forth. Here's that same map just showing Europe. As you can see, areas around Southern Europe have more lightning than Northern Europe, although there is certainly lightning risk throughout Europe and throughout the world. And here's a similar map for the United States. So, does grounding make a tank safe? Some folks believe that their tank is completely safe as long as it's well grounded. Well, as a matter of fact, lightning safety for tanks is not dependent on tank grounding. The occurrence of sparks and rimfires is not dependent on grounding resistance. Furthermore, the presence of a membrane under the tank has no impact on lightning-related occurrence. A tank is naturally well grounded if it's resting on earth or a concrete foundation. The most important thing you can do to improve the safety of the tank is to bond its roof and the shell. This location is the worst place to have arcing because vapors may accumulate along the roof shell seal. Therefore, it's essential to bond the roof and shell of any floating roof tank to reduce or eliminate arcing between the roof and shell. There's essentially three ways to bond the roof and shell. You can use a shunt, which is a short piece of steel that's connected to the floating roof and presses up against the shell. Number two, you can use metallic seals around the roof perimeter. Or number three, you can use a bypass conductor, which is a fancy name for a conductor whose one end is attached to the top of the shell and the other end is attached to the roof. It's named a bypass conductor because the conductor literally bypasses the inside of the tank shell. And we'll have more information on that in a minute. So the problems with number one and number two, shunts and metallic seals, are several. For example, they are dependent on spring tension for contact, meaning that shunts and metallic seals are pressing up against the inside of the shell. Number two, petroleum deposits like wax and tar and other gunk that's typically found in crude oil tend to accumulate on the inside of the tank shell. These materials have high resistance and therefore make the connection a high resistance connection. Also, some tank owners paint the inside of the tank shells, and this paint would be an insulator and cause a high resistance. And number four, a floating roof is not always centered within the shell. This means that you could have gaps between the roof and the shell. With shunts, regular maintenance is required because the shunts typically have a buildup of tar and wax and other things found in crude, and they could be a source of arcing between the roof and the shell. Here's some illustrations of those problems. Here we have a typical floating roof tank, and as you can see, we have rust on the inside of the shell, and that means the shunts between the roof and the shell would have a bad connection. As I said, many customers paint the inside of the tank, and that increases resistance. Also, there can be gaps between the floating roof and the shell, as you can see on the insert. If a tank shell is out of round, you could have a case where the shunt is not making contact with the inside of the shell. So what we have here is a gap between the roof and the shell, which means it's a poor electrical bond. Several years ago, the API did some testing, and the API testing proved that shunts will arc under all conditions. Doesn't matter if they're clean or dirty or well-maintained or whatever. They will arc under all conditions. This is a photograph of a test done with a simulated shunt pressing up against a piece of bare steel. Both the shunt and the steel were clean in this test, and simulated lightning current was passed through the shunt. And as you can see, we have a shower of sparks between the shunt and the steel. So the bypass conductor bypasses the seal around the floating roof. There's basically two categories of bypass conductors. You can have a conventional or a retractable. A conventional bypass conductor is a plain wire or cable that's attached at one end to the top of the shell and at the other end to the roof. You can also have a retractable bypass conductor, which is a spring-loaded reel, very similar to a tape measure. The problems with conventional bypass conductors are that they're unnecessarily long, and when the roof is high, they would become randomly coiled and splayed on the roof. So remember from the previous slide that the tank is most at risk when the roof is high. Well, when the roof is high, you would have a situation like this with a typical conventional bypass conductor. As you can see, the conductor has to be as long as the tank height, but when the roof is high, that cable will coil and splay in a random pattern on the roof and thus create the high impedance connection between the roof and the shell. So the retractable grounding assembly was invented by LEC in 1999, and we currently have over 13,000 units in service. We have the strongest springs and the most corrosion-resistant retractable device on the market. Here is the primary reason why this product is so much better than a conventional bypass conductor. As you can see, when the roof is high, a retractable reel will be short and tight as compared to the randomly coiled and loose bypass conductor on the left. Here's a photo showing that same thing. As you can see in the photo at the top left, a bypass conductor is coiled and loose compared to the RJ conductor, which is shown in the bottom of this slide. Here's the math for you folks who like math. Let's say, for example, we have a 150-foot diameter tank that is 50 feet high and it's 80% full, meaning that the roof is 40 feet high. Well, a conventional bypass conductor would still be 50 feet long and would be randomly coiled on the roof. However, an RJ cable would only be 10 feet long, and it would have about 15% of the impedance of the regular bypass conductor. Less impedance means faster reaction time, which means faster equalization of the two surfaces, which means a reduction or elimination of any arcing between those two surfaces. So both the API, which is the American Petroleum Institute, and NFPA, the National Fire Protection Association, recommend bypass conductors on floating roof tanks. They recommend that bypass conductors be installed no more than every 100 feet or 30 meters around the tank circumference with a minimum of 2. These bypass conductors are easy and inexpensive to install on both new and existing tanks. Furthermore, these standards say that the bypass conductor should be as short as possible, and please know that a retractable conductor is the shortest possible bypass conductor. So, in summary, tank fires are not uncommon, and lightning causes about 1/3 of all tank fires. Number two, as the weather changes, lightning rates are increasing worldwide. Number three, conventional roof-to-shell shunts, metallic seals, and bypass conductors provide high impedance connections, which is not what we want. We want a low impedance connection. Number four, the standards do recommend the installation of bypass conductors on external floating roof tanks. However, it is LEC's belief and recommendation that they be installed on all floating roof tanks for maximum safety. And number five, the RJ provides the lowest possible impedance bond between the roof and the shell. So here is my contact information. I would welcome any questions. And you can also reach me through the provider and moderator of this video. So while I've been talking, some questions have rolled in. So let's get to those now. The first question, on a bulk floating roof tank, what is the main down conductive path? So this person is asking, if lightning were to strike a tank, how does that current flow down to Earth? Well, lightning current by definition has to reach the Earth, and it would get there by flowing along all surfaces along the tank. So that means down the shell, across the roof, to the other side of the tank, and so forth. Basically, the entire tank would become energized if it were struck by lightning. And that lightning current will flow across the tank seeking Earth. Number 2, is there a resistance value that the bypass conductor should meet? Yes, the American Petroleum Institute and the Energy Institute advise a maximum resistance of a bypass conductor to be 30 milliohms. Number 3, how do you test an RJ when it's been installed and how often? Well, we don't recommend testing RJs after they've been installed because testing them electrically requires them to be tested with a multimeter, which injects current into the device, and current and petroleum storage don't mix. So we do recommend that they be visually inspected once a year to make sure the cables are intact and there's no corrosion on the connections. And number 4, what does it usually take to install an RGA, and can it be done on a live tank? Yes, 2 men can usually install an RGA in about 2 hours. It requires holes to be drilled or punched into the top rim and also on the chrome dam on the roof. This can be done on a live tank by using a punch rather than a drill, and it would also be a good idea to have some type of nitrogen bath or some other kind of non-flammable environment, so to ensure that no sparks are produced when you're creating these holes. Thank you for watching and listening to this presentation. I hope you found it informative. And again, you can reach me through my contact information shown on the last slide, or through the provider and moderator of this video. Thank you very much.